Welcome to The Explainer. Today, we're taking a really fascinating journey that mirrors the actual real-world life cycle of app development. We're going to start by looking at how you add flashy cutting-edge features, specifically a voice assistant. But then, we're pivoting sharply to the reality of what happens when you add all those great features. We're talking about the absolute need to achieve heavily optimized, blindingly fast code. Because, it's one thing to make an app smart, but it's a completely different beast to make it run to absolute perfection.
So here's our roadmap for today. First, voice assistants made easy. Second, the need for speed. Third, avoiding expensive operations. And finally, profiling with dev tools. Let's get right into it.
Okay, let's dive into this. Part 1, voice assistants made easy.
The era of typing is quickly making way for talking, right? But for developers, integrating voice can honestly sound a bit intimidating. Well, the great news is, to build a working voice assistant in your Flutter app, you absolutely do not need a massive machine learning team or some custom-built speech model. If we just break down a voice assistant into its raw components, it's essentially 4 basic steps. Step 1, permissions. You physically need microphone access to capture audio. Step 2, speech to text. We take that audio and turn it into readable text using existing ecosystem packages like speech_to_text. Step 3, logic. This is your app's brain, matching that text to a command or maybe sending it off to an AI model. And finally, step 4, text-to-speech, using a package like Flutter_TTS to give your assistant a voice to talk back. You're literally just acting as the architect here, assembling these existing blocks. Now, in practice, assembling these blocks does come with a few quirks. For instance, skipping runtime permissions in your Android manifest or info.plist, that is literally the #1 reason these features fail silently during testing. You also really need to know the quirks of the platforms. Android, for example, stops listening very quickly after a user pauses, and you can't really change that. So to keep your UI feeling responsive, you're going to want to use partial results so that the text appears live as the user speaks. Oh, and always check is available before starting. Plus, if you're supporting regional languages, for sure test on physical devices, because language support depends heavily on the device's operating system, not the plugin itself.
Moving right along to part 2, the need for speed.
So, we've just added a brilliant voice assistant. But adding cool, dynamic features can silently bloat an app. The UI gets heavier, layouts get complex, and suddenly, your snappy app feels kind of sluggish. Which brings us to a bit of a harsh reality check. Let me throw a number at you: 16. In the world of mobile app performance, 16 milliseconds is your magic number. It is the exact, non-negotiable deadline you have to build and render a single frame on a standard 60 Hz display. Miss this deadline, and your user sees stutter, lag, or, what we call jank. To be on the safe side, Flutter actually gives you a breakdown for this budget. You should aim to execute your build phase in 8 milliseconds or less, and your render phase in 8 milliseconds or less. So why does pushing this time down matter so much, even if you're already hitting that 16 milliseconds? Well, rendering faster saves a ton of battery life and prevents the device from thermal throttling. Furthermore, as 120 frames per second devices become the new standard, that 16 millisecond window gets sliced completely in half. So you're really future-proofing your app by optimizing it today.
And that perfectly sets up part 3, avoiding expensive operations.
So what exactly causes an app to blow right past that strict 16 millisecond deadline? Usually, it's not your simple UI elements. It's the hidden, expensive layout passes and heavy rendering costs that we introduce without even realizing it. And one of the absolutely biggest offenders here is a method called saveLayer. When this gets called, it allocates an off-screen buffer to draw content before composing it onto the screen. This triggers a render target switch, which is highly disruptive to your device's GPU.
I actually love how the official Flutter documentation explains this. It says, the GPU wants to run like a fire hose, and a render target switch forces the GPU to redirect that stream temporarily and then direct it back again. It's such brilliant imagery, right? It paints a perfect mental model. You are literally kinking the hose of your device's processing power, and that completely destroys your rendering throughput. But here's the tricky part. You might actually be calling saveLayer without even typing it. Certain Flutter widgets trigger it silently right behind the scenes. Using a shader mask or a color filter are the usual suspects here. But watch out, because even a simple chip widget can trigger it if its background isn't fully opaque. Even text widgets with an overflow shader can cause this kink in the fire hose. So if you ever suspect hidden overlaps or heavy rendering, checking DevTools for saveLayer calls is absolutely your first line of defense.
Beyond rendering, I want to rattle off 3 rapid-fire optimizations to help protect your performance budget.
First up, in Dart, use string builder inside loops instead of the plus operator. This avoids creating massive amounts of unnecessary string objects. Second, try to avoid using the opacity widget or clipping operations when you can honestly just paint a shape with a semi-transparent color instead. And third, when dealing with long lists or grids, always use lazy builders like List View Builder. Doing this prevents intrinsic passes, which is this incredibly expensive layout process where the framework asks every single unseen cell in a massive list for its size before it even draws the screen. Basically, be lazy. It's great for performance.
All right, bringing it home with part 4, profiling with DevTools. So let's move from theory to practice. We've covered the theory of what makes an app fast and what bogs it down. But how do you know if your app is actually performing well? The DevTools CPU profiler might look like an intimidating wall of data at first glance, but it's really just 3 main views. The bottom-up view flips the script. It puts the deepest, most specific methods right at the top, which makes it perfect for finding that single, individual, expensive function. Then there's the call tree view, which is top-down. You start at the top of the app and drill down to find exactly which path is eating up your CPU. And finally, the method table removes the stock entirely, giving you pure raw statistics on how much total time a method consumed.
Now, when using the CPU profiler, you also have to choose your sample rate, and there's a vital trade-off here. A low CPU sampling rate sitting at 1000 Hz is coarse-grained. It impacts your app's performance very little while profiling, and the memory buffer takes a lot longer to fill up. On the flip side, high sampling at 20,000 Hz gives you incredibly fine-grained data, but, and this is a big but, it constantly interrupts the virtual machine to take those samples. That can actually slow your app down during the test and overflow your data buffer really quickly. So just remember to choose the tool that fits the specific bug you're hunting. Which leaves us with this final thought. You know, you can implement every single optimization trick we just covered, lazy builders, avoiding save layer, keeping builds strictly under 8 milliseconds, but until you actually measure it, it's all just a theory. So, I have to ask, are you guessing your app is fast, or are you proving it? I highly challenge you to take the concepts from this explainer, go open DevTools on your current project, and prove your app's efficiency today. Thanks for joining me on this journey from features to perfection.